In this tutorial, we'll explore modeling dynamic risk with specific emphasis on GARCH models. First, let's begin by understanding the benefit of modeling risk dynamically. One concept, often observed in financial returns, is volatility clustering. In the return series shown, we can quickly see periods where volatility has increased and stays elevated for several weeks or months, and periods where volatility diminishes and remains low for long periods of time. Moreover, these spikes in volatility tend to correspond to bear market conditions as observed in the 2008 financial crisis. A well-known measurement of dynamic volatility is the VIX, or Volatility Index. Shown here, the VIX measures implied volatility from option trading to yield a dynamic measurement of risk. Notice the peaks correspond with our clusters of high volatility and downward market trends. Further support of this relationship is observed from the strong negative or inverse relationship as measured by the correlation between the S&P 500 and the VIX. Therefore, being able to measure risk dynamically can help us understand current market risk environments and potential market trends. So far, we've already touched on one measurement of dynamic risk, the VIX. The disadvantage of the VIX, however, is that it only relates to changing risk in one particular market. Other approaches include using rolling windows for volatility or exponential moving averages on volatility. We'll focus on a specific model type, GARCH. GARCH stands for Generalized Autoregressive Conditional Heteroscedasticity. The formula was developed by Robert Engel and Clive Granger, who won the 2003 Nobel Prize in Economics. Homoscedastic is a fancy word that means homogeneity of variance, or in other words, constant volatility. Heteroscedastic is the opposite, dynamic volatility. Conditional implies that the current risk level is based on information in the period before it. Most traditional volatility measurements are unconditional, meaning they simply take a time series and compute volatility once without taking other prior information into consideration. An example GARCH model is shown here, which is called a GARCH 1-1. We'll explain what the 1-1 portion means in a moment. The left-hand side is the current time period, T's, volatility squared. On the right-hand side, the first term in the model can loosely be understood as the long-term average volatility. This would be the closest equivalent to a traditional unconditional volatility. The second term implies that the current volatility level is related to the previous time period's squared error. Error here is simply a deviation from the mean. In other words, yesterday's return minus the long-term average return squared. The third and final term is the previous estimate of volatility squared. This acts similarly to a moving average of volatility. This may be visualized with the following chart. The process is iterative, with each day's equation based on the previous day's estimates. The parameters may be estimated using maximum likelihood estimation. As mentioned before, the GARCH 1-1 model is named since this equation is based only on the previous time period for both the squared error and prior volatilities. If we added a term for 2 time periods on each, then we would have a GARCH 2-2 model. The error terms may be modeled using a normal distribution or fat-tail distribution with certain considerations made. For now, let's show an example of a GARCH model applied to our time series, with risk measured using expected shortfall. Combining this GARCH model with a fat-tail distribution, such as skew T, and the expected shortfall measure, we produce the following. Notice this risk estimate now dynamically tracks our clusters of volatility. In comparison to our previously mentioned VIX, we see while inverted, the overall shape and transitions match rather closely. The advantage using this methodology is we may now produce dynamic risk measurements on any security of interest. This completes the dynamic risk tutorial.